Okay, so having proved that this is the point is going to help us to understand compactification of modulus of genus 0 n pointed curves for n bigger than 3. So let us do this case n equal to 4 now. So M04 parameterizes, this notation I write is wrong. The space is a point. And the space is equal to realization of the functor curly M03 at spectrum of C. And whatever underlying scheme over complex numbers you put in here, it's not going to change it. The underlying coarser space is going to be the point. Okay? So that's what we proved.
But
so, yeah.
I remember for genus 0 case, coarse modulus space are same as fine modulus space. So
that's right.
We don't need to
distinguish
these two.
Yes. But because we discussed the space as realization of the functor over the ring, we actually put a proof last time that it doesn't matter what ring you put. So always get the point. Okay, so M04 parameterizes 4 distinct points, right? 4 distinct points on P1. Okay, so basically M04. So 3 points of P1 are the canonical points 0, 1, infinity. So the third point need to be outside of it, right? The fourth point. So it's going to be a P1 minus 0, 1, infinity. Otherwise, it collapses to one of the canonical points of P1. So, okay, how is that? So this is how it is. So let's say this is the P1. And then you have the 0 point, and you have the 1 point, and you have the infinity point. Okay? So your moduli space would have configurations of 4 distinct points, right? So this is how it's going to be. So the only way that you can have such a situation is that you would have 2 points like this. So 1, 2, 3, 4. Right? Or you would have, you can change the labeling of these points 1, 3, 2, 4. Or you would have 1, 4, 2, 3. So this is what your moduli space looks like. The fiber of the moduli space over these 3 points, canonical points of P1, gives you the choice of movement of this 4th point on the second branch, right? So now if you look at this curve configuration, this is a P1 and this is a P1, this is genus 0. Each genus 0 piece is reducible. Each genus 0 piece has at least 3 special points. 1, 2, 3, 1, 2, 3. So it's all okay, and it is based on our recipe, except you can just shuffle around label of the points. So those are, as we discussed, automorphisms of this, and automorphisms of this curve has to do with permutation group of irreducible components and the permutations of the nodes, and this is exactly what we are getting in here. Okay. All right, so how about for n bigger than 4? Same exact situations. You have n points, you have 3 special points of P1, and on each one you need to somewhat toss out configurations of some number of points in here and some number of points in here such that their sum equals n. Making sure though that each component is stable, meaning at least needs to have 3. Okay, so for M0n, consider this configuration. So I'm going to put P1 to PA. I'm going to put P. So how should I write it? Actually, I'm going to put some number of A points in here. Yeah, and then A plus 1. And then Pn. I'm going to call this thing B. This number of points in here, A, this number of points in A. There is a divisor DAB in M0n for each partition AB of number n, integer n, okay, into two disjoint sets. Does that make sense or not? Well, the moduli space is a P1 minus these three canonical points. On each one of these canonical points of P1, you're tossing out configurations, possible configurations. Each point of this P1 is a curve configuration. So this P1 is not a normal P1. This P1 is the moduli space of pointed curves. So each point is a curve together with at least 4 points on it. Okay, on this one, you see this configuration. Okay, the total space of this family is your moduli space. When you look at the fiber of your family over the 0 divisor in P1, this is a divisor in your moduli space, right? So because this is the fiber over a point of P1, it's a divisor, one dimension less. Same thing, one dimension less, one dimension less. So, okay, 0 is a divisor, 1 is a divisor, infinity is a divisor. These are divisors. Each divisor of P1 is representative of this curve configuration. And each point of P1 is a divisor. And each point of this P1 is a curve configuration with 4 points on it. So as you can see, your moduli space has these divisors, and each divisor is basically understanding how to mutate these labels. Same thing in here. On the P1, which your moduli space will be, for every partition, for every way of basically splitting this thing, this integer n, into two disjoint sets, you will get a curve configuration like this. And this is one of the possible configurations, right? So this is a point of P1. So this point of P1 is a divisor in that P1, so it's a divisor in your moduli space. So each time you give me a partition of n, I have some divisor, which is a point of P1, corresponding to this picture. Okay, so that's what the modular space is. All right, a generic point DAB is represented by and here, by the way, we get this because this is the only possible partitioning of 4, basically. All right, the generic point DAB is represented by two lines meeting transversely. As above, with distinguished smooth A points and B points on its branches, on each line, respectively. Okay, so that's what your moduli space is. So that is M0n. Okay, so now what about forgetting number of points? I have configurations of curves with n points in here. I can forget some number of points, and I can go down to curve configurations with n minus 1 points. Is there any communication between their corresponding moduli spaces via forgetting the nodes? All right, we would like to note that. So denote MGA, okay, moduli space of genus G curves, where A is the labeling set of n points on the curves. Okay, P1, P2, Pn, that's label set A. And now let B in A, a subset, be a sublabeling set. Then there exists a forgetful morphism, which takes you from M bar GA to M bar GB by forgetting whatever number of points are not in B. Okay? So forgetting points in A minus B. Okay. On the open locus, so I would like to say, what does this forgetful morphism look like? All right? So each moduli space is compactified. So you have this moduli space with its interior. This is M bar GA. And you're looking at this forgetful map, this moduli space in its interior, M bar GB. Interior here is MGA without a bar. Interior in here is MGB without a bar. This is boundary of M bar GA. This is boundary of M bar GB. Okay, so you have this. Now you would like to understand this forgetful morphism. Okay, on the open locus, this forgetful map, is the obvious one. Right? Why? Open locus is just configurations of smooth curves, non-singular curves, algebraic curves with n points on them, labeled by the set A, and then whatever number of cardinality of set B is, n points on them after forgetting the points. That's it, nothing really in particular. All of the exotic structure of this thing happens on the boundary, because when the curve becomes singular, the boundary understands how singular it will be. And it's on the boundary that your curves need to be stable. So as you take a point in this boundary and you would like to send it to a point in here, you would like to make sure that you start from a point on the boundary here, which is a stable curve with n points, and you want to land on a stable curve with m points on the boundary in here. So, of course, if I mess with the node configuration, special point configurations, the curve might not become stable necessarily. So those pieces of the curves in here, which become unstable after removing a point or forgetting a bunch of them, collapse and just go away when you land on here. Otherwise, you will not land on a stable curve in here. So if you have a stable curve in here, this map is only well defined if you land on a stable curve in here. So all the unstable components of the stable curve in here will go away. So this forgetful map not only forgets the nodes, but also forgets the unstable components. So they collapse. So let's see. On the boundary, removing points might lead to instability or instability. For instance, consider this situation here. I can start from M05 and I can go to M04. I can ask my labeling set to be 1, 2, 3, 4, 5, and I can ask my labeling set B to be 1, 2, 3, 4. Here. Okay, so what is this map pi? By the way, let's just call the forgetful map projection pi. Okay, so I can look at M0n. M0n in general is configurations of reducible two lines with whatever partition I choose to toss out n points on it. So that's all I need to do here. So let's just take a possible partition in here. So I can start like this. 1, 2, 3, 4, 5. This is okay. If I have two genus 0 curves meeting like this, there's at least 3 points in here, there's at least 3 points in here, the whole thing is stable. Because this is singular, and after normalization, each component has minimum number of special points on it. Okay, now let us forget this labeled point P5. When I do that, I will get to 1, 2, 3, 4. This whole component becomes unstable because after normalization, this whole component has the preimage of the mark point, which is okay, but has the preimage of node, and that's only 2, and it's genus 0. So it definitely, the map that looks at automorphisms of this P1 will have infinitely many possibilities. Because as long as you have 3 points, until you have 3 points, you have all the possibilities by multiplications by C star to rotate this thing around. When you fix 3 points, it doesn't work anymore. So it's not finite, and this is unstable. So this collapses, collapse, and it becomes something with 4 mark points, which is stable. So this whole component collapses, this becomes like that. This point is an honest, this curve configuration is an honest point on the boundary of M04. And it could be an image of the process of forgetting a point from M05. In other situations, or I can look at other curve configuration, which is genus 0 and has 5 mark points on it and is stable. So it is the point of M05. You might say that, why is it we are only interested in M03, M04? Because M03 and, do I have it? Yeah. M03 and M04 are going to be building blocks for understanding M0n. For any subset A, B, C, D of 4 integers, and n, there exists a morphism from m bar 0 n to m bar 0 I j k l. The inverse image of a point ij and then kl in m0 ijkl, all right, is given by sum of divisors DAB such that A union B is equal to N. IJ is in A and KL is in B. Is this the case in here or not? Well, M04, I have the set of integers 1, 2, 3, 4. So the pre-image, as soon as you give me the set of integers in here, I can partition 4, number 4. 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3, so on and so forth. The pre-image of this thing is all the possible configurations in here such that 1, 2, whatever partition is on one of the branches and the other one is on the other branch, but I need to add what I'm forgetting to it, right? So look at the pre-image of this guy here. You see? I add the number 5 to it. So 4 is part of, I could have picked 3 and 4. So 4 and 3 will be here, but I need to add the number 5 to it. And the same thing with this one. If I take 1, 2, 3, 4, I give a partition 1, 3, and 2, 4, and I look at the pre-image of this in there, I will get 1, 3, 5. So I can get all the sum of divisors such that 1, 3, and 2, 4 are parts of A, 1, 3 is part of A, and 1, 2, 4 is part of B. But A plus B is the number n. So this is how the pre-image looks like, right? Because we are forgetting numbers. Okay, so that's how it is. And then the fact that 3 points in bar 0 I j k l isomorphic, which is isomorphic to P1, are linearly equivalent tells us that when I look at the fiber of the moduli space on these configurations, the divisors I get on the moduli space of n points on the curves, those divisors are going to be linearly equivalent to. So it tells us that their inverse image in m bar 0 n are linearly equivalent as well. Okay, so that is sum of all partitions A, B of n points where such that with the condition that because I'm going from n points to 4 points, I'm forgetting some of these and some of the points in here and some of the points in here, but I'm keeping track of only 4 of these points given the partition. So I and j I would like to be in A, and k and l I would like to be in B. So this is going to be equal to summing over I and k in A and j and l in B of DAB, and it's going to be the same as the other partition I and L in A and j and k in B DAB. Okay, is the picture clear? So we start from M03, it was a point. Then, sorry, I need to really cut this. Oops. How can I? I was taking pictures. All right. So you have M03, which is a point. M04 is the choice of a 4th point on P1. So the point has all the possibilities on P1. So M04 is a P1. And the point can land on outside of these 3 special points. Every point of this P1 I look at, I see curve configurations. And I just need to toss out 4 points on them. So those are the divisors. All the ways that you can partition 4 as long as the curve configuration is stable, those are the divisors in that M04 P1. Okay, now you have this P1, M04. Now you want to go from M04 to M0n. M04 is a P1. Now to go back to M0n, you need to add points. Okay? On M04, you have these linearly equivalent points of P1. The 3 points are linearly equivalent. And the 3 points on M04 are all the ways that you can toss out IJKL, right? We showed the pictures. As points in P1, these are linearly equivalent. Okay, when I look at the preimage of these things in M0n, I look at the curve downstairs. Ij are next to each other, Kl are next to each other. I'm looking at curve configurations with partitions AB of n such that Ij is at least in A, Kl is at least in B. And I can permutate Ij, Kl, and I look at the preimages. The preimages up there are also going to be divisors because this is a projection. And so those divisors are also going to be linearly equivalent. All the possible ways that you can partition n to A and B with this condition is the same as all the possible ways this is the case and all the possible ways this is the case. Okay? So this is how you would understand M0n. Okay. Remark. Oh, by the way, this sum, these are divisors, right? What you didn't ask me what this sum is. Each divisor is a space, right? It's a codimension 1 subspace of M0n. So what does it mean summing them? What does that mean to you? Summing the spaces? Yeah, so but what does it mean sum of the divisors equal to? What does that mean? If I want to talk about the space, I would say they are isomorphic. I wouldn't call them equal. But here I'm saying they're linearly equivalent. So linearly equivalent in where? As in the category of the spaces? In the group or ring that understands these spaces as elements. And what is that? The Chow ring. So this equality holds true in Chow ring A1 of M 0n. Otherwise, doesn't make sense, right? Sum them or, but in the child ring you can. And child ring is a ring. You can have addition and have multiplication and all of that. Multiplication is the intersection of the spaces. Addition is the union of the spaces. Okay, so all right. So remark, Sean Keel has shown that classes of these divisors, so yes, so the child ring is the class of divisors. Classes of these divisors generate, these divisors DAB generate the whole child ring of M bar 0n. Okay? Think about cohomology theory of P1 or Pn. If you have Pn, projective n space, you can start from codimension 1 divisor in there, hyperplane, and hyperplane section of Pn. That has a class, H, and then you multiply it with itself. It means intersecting it with itself. H times H is codimension 2, H times is codimension 3, and it can go to n. And the nth product of hyperplane class with itself is the point class. So it's a fact that in projective space, the hyperplane class generates the whole child ring. Any class of codimension m you pick, you can always write it in terms of a linearly in terms of self-intersection of hyperplane class with itself. Same thing in here. These divisors generate the child ring. And this tells you that the codimension of the class is 1. The degree of the class is the codimension of the subvariety. This is a divisor, codimension 1, so degree of class. That's why it sits inside degree 1 Chow cohomology. All right, so that's what we can tell about M0n. So understanding M03 and then M04 and then M04n, based on that is possible. Okay. Okay, so that's that. Now, I talked a lot about stable curves. Okay, so I think we know as much as we want about the stable curves. We have some playground, we can play with them, we can even draw pictures of these stable curves, but I mean, these are genus 0. The possibilities for them is much less, but as soon as you look at genus 1, then it's much more possibilities, how I can get a stable curve configuration with genus 1 components. Good. So now we can talk about embedding curves into the ambient space. So string theory actually tells us that we would be interested in Riemann surfaces which are embedded in some ambient space such that the Riemann surface is pinned at certain points and is undergoing fluctuations, deformations, algebraic deformations. So let us talk about not just honest curves, but curves after mapping them into an ambient space. Stable maps. Okay, let X be a smooth, projective, variety, and beta in degree 2 homology, Chow homology of X is be given as a class, homology class. Let M Gn X beta denote the following. A set of isomorphism classes, of pointed curves C P1, P2 up to Pn, where C is a projective non-singular curve of genus G. P1 and Pn, P1 to Pn are disjoint points of C, The fact that C is already non-singular tells you that P1 to Pn are also not smooth. So there's points of C. And F from C to X is a morphism such that the push forward under this morphism of homology class of C, curve C is equal to beta. Okay, so as we discussed, when the string world sheets are being made, they become singular, but also their topological structure undergoes deformations. They may become like a torus, they may become a genus 2 surface, and their homology also might change because they're undergoing deformations. They might break apart, and so many things can happen to them. So now we are looking at the moduli space of not just the honest curve, but also the curve embedded inside ambient variety, together with the map. So this is the map. And we would like to stratify this moduli space. Each component of this moduli space, I would like to parameterize a particular set of curves with fixed Chern homology class. So I fix the homology class, and then I can look at a particular component of the moduli space of all possible curves in X. Of course, later I will add over beta, and I will get all the different components.
So here actually the C point of this movement.
That's the C point of this moduli space. It's the isomorphism. The C point of this moduli space is the isomorphism classes of these things. The moduli space doesn't like to have many copies of the same curve, but looks like I look at the equivalence class of those things, and that's a point in that moduli. So the C point is isomorphism class of this. Okay? So already tells you that if you really want to open this thing and do engineering on the moduli space, to kind of see what the moduli space is really, these curves might have also automorphisms. There is a group that captures their automorphism. The moduli space needs to at least the orbit space of that group, because automorphisms are isomorphisms. So locally, this moduli space should have quotient singularities, things like that. So it should be some locally could have a realization as a space or a coarse space associated to some stack, which is some space divided by some group, finite group. All right, so locally. All right, but we will discuss it. We will. It has orbifold singularities, for instance. Okay, so then the notion of isomorphism. Then F is isomorphic to F prime given, let's write it this way, given two such maps, F so let's write it like the C, P1, Pn, F from C to X, and C prime, P prime 1 to P prime n, F prime from C prime to X, we say that F is isomorphic to F prime. The maps are isomorphic if and only if this condition is satisfied, if this diagram is satisfied. So you have the system of n-pointed curve, and you have the system of n-pointed curve. You send both of these things via your maps to your variety X, and you would like to have a morphism between them, and you call them this morphism G, and you like this diagram to be commutative if G is sending C isomorphically to C prime, Pi, and under this map Pi's go to Pi prime, and F prime OG is the same as F. So the two maps, not the stable, the maps in this space are going to be equivalent to each other if the curves are isomorphic to each other, and if the points markings in here are mapped to the markings in here, and if you map the markings to these markings and then look at where the points land inside the ambient variety, is the same as the image of where the points land in the ambient variety under F. So compatibility between where the points are being sent.
So can we take the special ambient variety X and the beta such that this notation, this MG and X beta, to coincide with the old modular space MGN?
If you want to go from this space to the old moduli space MGN, you need to forget the map. Yeah. So, for instance, let's say I give you a line with local coordinates x. I give you a map, f of x, x squared. You see, the line intrinsically is a straight thing, but after I apply the map to it, the map is a quadratic map, so it makes it like that. And then this y equal to x squared is embedded inside some ambient space. So as you can see, the intrinsic object, the domain, is a line, a straight line, but the image is a curved thing. So if I forget the map, I should land on the line, right? This is what's happening in here. The map changes the geometry of curve after it's being sent to the ambient variety. So this moduli space understands more. The domain curve it understands, the markings on the domain curve it understands, but also it remembers what the map is doing to it. Okay? Now that's a very simple example. And MGN itself is parameterizing curves up to dilations and up to automorphisms. Okay, so it's not going to be any difference between a line and a curve in MGN. But there might be many more differences. And those differences you will see. It has to do, and we will discuss, especially when we are looking at singular curves actually. When you look at singular curves, you see that there is a notion of stability for this map too. So you can forget the map, and you will see that stable map can map to stable curve, and this is something non-trivial. Because their notion of stability are a tiny bit different from one another.
So actually this baby we call it a stable map, right? So
it's not yet stable. Why is not? Because the stability is about how controlled the singularity of that curve would be.
okay.
Here,
Yes.
it's just a smooth curves.
Yeah, it's already stable.
Yeah. This space, I didn't say it's compact. It's an open set. It's just a set of isomorphism classes. So we don't yet know about the stability of these. in this picture. Okay, so that's that. Good. But this topic is about the stable maps. This is not a stable map. Okay, maybe this is what makes you make mistake. Yeah. Okay. This is the chapter on the stable maps. Okay. Yeah. But soon I will compactify this space, and then we can talk about the stable maps. Okay. So that's that. Okay. So if beta, the curve class, is not equal to 0, then mgn x beta is going to be empty unless beta is a class of a curve in X. You know that you can pick cohomology classes in cohomology theory of a variety. Whether or not this cohomology class is associated always to an algebraic subspace is not known. If it is not algebraic class of an algebraic curve, the moduli space for that particular choice of a class is going to be empty. Also, if genus is equal to 0, mgn x beta is going to be empty if beta is not equal to 0 and x does not contain any rational curves. Genus 0 curves are rational curves, and if the genus is 0, beta is not equal to 0, and x does not contain any rational curves, examples of which do exist, then this moduli space clearly will be empty, because those are rational curves. Okay, the smooth genus 0 curves. Okay, and then fact 3. Maybe I just write it in here. There exists a compactification mgn x beta lands inside m bar gn x beta, parameterizing what is called stable, not just maps, but stable maps. But I need to tell you what a stable map is. Okay, definition. Stable map. Okay, stable map. An n-pointed stable map consists of a connected curve, marked curve, C with n markings on it. Okay, anamorphism, f from C to X. Let me see, is this better if I use this one? Oops, very difficult. Is this better? Anamorphism C to X satisfying the following properties. Okay, what makes this stable? One, the only, you see, stability is a way of controlling singularities, really. The only singularities of C are ordinary double points. So locally quadratic singularities, ordinary double points. 2. P1 and Pn are disjoint ordered smooth points of C. Okay. 3, if C is a compact, if C is a component, if Ci is a component such that this particular component is isomorphic to P1, so it's a genus 0 component, and F is constant on Ci, then Ci contains at least 3 points, 3 special points. Okay, so if the morphism sends this component to a point and the component is genus 0, it needs to have at least 3 special points. And the special points in here, i.e. Nodal, nodes, or markings. Okay. 4, fourth, now think about it. If F is sending this to a point, and this genus 0 component doesn't have at least 3 special points, I can get many, infinitely many copies of such maps. How? I look at the automorphism of this, and I apply F to it. That's a map. Another automorphism, and apply to F to it. Another automorphism, I get many, infinitely many possible maps. So in some sense, this recipe is to guarantee that as a whole, this configuration being sent into the ambient algebraic variety also has finite automorphisms. This is basically going to guarantee you that. Okay? All right. So number 4, if C has arithmetic genus, genus 1 and n is equal to 0, then F cannot be constant. Be constant. This is equivalent to saying if there exists some E in C, a component, such that genus of this component is equal to 1, and f is mapping this component to a point, then E needs to have at least one special point. When you look at constant maps, you can dilate them. If this guy doesn't have any markings on it, and it's a genus 1 thing, then f cannot be constant. Because then again, I would be able to dilate this thing, and that gives me dilations of my map. All of them will be constant. I get infinitely many possible configurations being sent to X, and that's not what I want. So, how can I avoid it? Either f cannot be constant, in which that solves the problem, or if it is constant, I need to make sure I don't get infinitely many copies of such maps. In which case, we have seen it. If I have a domain curve with genus 1 and I put a special point on it, then that fixes the automorphism. That means a finite automorphism. So because the automorphism of the map is first look at the automorphism of a curve and then compose with the map, that also gives you finite automorphisms for map. It kind of respects really the stability of the curve itself. But here the only caveat is that now the map can be constant or non-constant. So we are adding this to our stability criteria. Okay? So that's that. This is what a stable map is. So here is a theorem, Alexeyev, Fulton. It's actually done by Alexeyev, also jointly by Fulton and Pandey. If X is projective, and beta is not equal to 0, an element of integral homology of ambient variety, integer valued homology of ambient variety, then there exists a projective coarse moduli space M bar Gn x beta, where M bar Gn x beta is a scheme together with a natural transformation, together with a functorial natural transformation phi equal to the functor M bar Gn x beta, which you can apply to a scheme, to the functor hom comma straight M Gn x beta. And this hom is over the category of schemes over complex numbers. All right. Pay attention. So this is a functor. This is a functor. This functor you can apply on any, feed it by any scheme S, parameterizing scheme S, and it produces for you families of maps from curves of genus G with n markings to X, parameterized by that scheme you're applying it to. This is also a functor. And this actually tells you exactly communication between a space that represents a functor and a functor. This is the moduli functor. This is the moduli space. When you look at some scheme S, for every point of that scheme, you will get one of those maps. But this is exactly what this HOM does. If you put S in here, it's a space, it's a scheme. Every point of this is mapped to a space. But the points in this space are those families, are those curves. So this is exactly that. So this is how a space co-represents a functor. So these people actually show that there is a space co-representing this functor. The functor has an algebraic definition. You can always define it, no problem. But whether or not there is a space that always satisfies this identity between functors, and because this is identity between functors, it's called a natural transformation. That needs proving. So this is the result of these two. And this natural transformation satisfying the following properties. Okay, what is the property? If I apply this natural transformation to spectrum of the algebraically closed field C, it will get a C point in here and a C point in here. So I will get a curve in here and I should get a curve in here, right? A map in here, stable map in here and a stable map in here. Now I can call this stable because I have put a bar. This without is just moduli space of maps. With a bar, stable maps. Okay, this will be curly M Gn X beta, spectrum of C, which is A point to HOM over the category of schemes over C, from spec of C to the space M bar Gn X beta is a set bijection, because it's a set, right? This space is an isomorphism, set of isomorphism classes, a set bijection. Number 2. So that's that. And then, first of all, this is number 1. Number 2, if S is a C scheme, meaning it's a scheme over complex numbers, that's what the C scheme is, and M and psi from M Gn X beta to HOM S is a natural transformation. Natural transformation of functors, then there exists a unique morphism of schemes. Let me call it gamma, which is from the space MGN X beta to S such that psi is gamma O phi. And gamma tilde O phi, where gamma tilde is homomorphism from MGN, from something to MGN X beta to homomorphisms to S. Consider this as the universal property of the moduli space or moduli functor. Okay. Yeah. So apply hom functor to this morphism and you will get what you want. So this is the natural transformation. This morphism is the natural transformation induced by gamma. Okay. So that's that. So there is a moduli space with all the nice properties that we want. There is a moduli space of stable maps that co-represents the moduli functor of stable maps, which is itself a two-category fibered over category of schemes over C with group-weight sections given by isomorphism classes of the n-pointed curves with maps into ambient variety X. Okay, so that's that. What else? Here's a theorem due to the Professor Kansevich, who is also a joint faculty of University of Miami. If X is projective, beta is not equal to 0, an element of integral homology, second integral homology of X, then the functor, curly M G and X beta is an algebraic stack. Proper over C. Furthermore, M0n PR beta is a smooth stack. So if you choose for your ambient variety projective space with this condition, it's a smooth stack. It's a smooth stack. Remember, a smooth stack is different than a smooth space. Okay. Every algebraic stack has an underlying algebraic space. And underlying algebraic space for mgn x beta is indeed mgn, straight mgn x beta. Okay, this is an algebraic stack. Examples of algebraic stacks are the Lie-Montfort stacks, quotient stacks, Artan stacks. These are examples of algebraic stack, but the very definition of algebraic stack itself is beyond that. It's more abstract than that. Examples of it are quotient stacks. Okay. All right, so let's do some examples and then maybe finish the session today with those. Okay, so here is an example. Examples of straight mgn x beta. One, let us pick x equal to a point. So you cannot map a curve with non-trivial homology class to a point, right? So beta equal to 0. Then m bar gn point 0 is what is it? Another point? Well, you just don't map them, right? Not only it's not another point, but actually it's a huge space. Just do not map them. 2. So if you forget the map, you still have the domain curve. A piece of information is staying there. So that's just the m bar gn itself. All right. X equal to PR, projective space. Then you can have pick for beta b times class of a line, and P1 in projective space. Then m bar gn PR d times class of a line is going to can be defined depending on d. For instance, example, m bar is genus 0, no markings, PR, this line is class of P1, right? P1 class of P1. Do you know what that is? Mm-hmm. It's genus 0. Mm-hmm. Yeah. So this is going to be you're sending P1s, embedding P1s inside PR. Not only it's curve inside an ambient projective space, but it's also a These are compactifications of vector spaces, right? Subvarieties. What's the space that parameterizes the subvariety of a given variety? Subvariety of dimension 1 sitting inside a variety of dimension R. Grassmannian. Right? This is the honest Grassmannian. Okay, so that's that. And then if I don't put any markings on it, it's just P1 itself is smooth, it's okay. So I'm fine with it. I don't need to worry about the stability of it. But then I can put markings on the curve. So I can look at M bar 0n PR with class of P1, and still I'm embedding P1s inside ambient projective space, but now I'm making sure that as I'm doing this embedding, I pin some points of it, so the number of possibilities is much less. Okay, so this is a locally trivial vibration over Grassmannian P1 sitting inside PR with fibers given by P1 and configurations of n-pointed curves. This is due to Fulton McPherson. Another example, this was an example A, example B, another example C of this same thing for the projective space. We can have M bar 0, 0, P2 with 2 times class of P1. So this is something that I need to, the interior of, I need to discuss interior of this, and to discuss the boundary. Okay. So this is curves whose homology class is 2 times P1. So can you guess what could be the homology class of 2 times P1? A P1 is like a hyperplane, right? It's like a plane. Degree 1 homogeneous polynomials. When you have something with 2 times class of that, it's a conic, right? It's a quadratic polynomial. These are conic sections, okay? So this consists of non-singular, interior of it, yeah. Non-singular conic curves. Inside P2. Unique up to equivalence. The conic curves are also isomorphic to P1. And inside the ambient projective two-dimensional space, there are divisors. Think about the example I just made you. You have the line, you have f equal to y equal to x squared. The x squared and the x-axis are isomorphic to each other, but one of them is a conic, one of them is not. Same thing with the projective space. So this is a smooth isomorphic to P1 divisor inside P2. And because its homology class is 2 times P1, it's a conical, degree 2. Okay, so that's the interior. And the extent and the boundary of it, so boundary consists of singular conics, D divisors as divisors inside P2, which are union of two lines intersecting or meeting transversely at a point. Okay? Why? Because we discussed it. When you're looking at the stable maps, the type of singularity of the curve needs to be at most ordinary double point singularity, and that's the only way that you can get for conic. So interior together with the boundary gives you the whole moduli space. So this would be M bar 0, 0, 2, P2, 2 times class of P1 is going to be the set of things like this, conics, plus set of things like this, which are sitting inside P2, non-singular conics, singular normal crossing conics. Okay, so yeah, so this is an example. Okay, and we will make more examples of these things later. All right, so all right, thank you very much. Let's meet on Monday, right? Monday, same time. I will mention more examples of these or singular possibilities. There's this double cover of P1, which I forgot to mention, but anyway, next time.